Alright, so let's talk about charge transfer absorption. So basically, when transition metal absorb light in the visible region, they become colored. So absorption results in the transition between electronic energy levels. So recall that a metal complex is composed of a metal that is coordinated to ligands, right? So absorption will occur when there is one. Let's look at it. So first of all, when there's transition between metal orbitals, right? So they did the transition that we saw the other time. So like this. So this is a kind of transition, right? So it occurs between the metal atoms, metal orbitals, right? So transition can also occur between the molecular orbital of the metal and the ligand, and vice versa. So this gives rise to the concept of ligand-metal charge transfer or metal-ligand charge transfer. So basically, metal-ligand charge transfer involves the transfer of electrons from the orbital with primarily metal character to another with primarily ligand character, right? So ligand to metal charge transfer is basically the transfer of electrons from this ligand to the metal, right? So let's look at this question. So the first question is the metal manganese and this are found in the same group on the periodic table. So basically on the periodic table we have manganese at the top, we have this to be lower, RE to be lower, right? So are found in the same group on the periodic table. So the ligand to metal charge transfer band for this and then this are recorded at this and this. So explain the trend in the ligand to metal charge transfer band. So basically what you need to note is that whether it is ligand to metal charge transfer or a metal to ligand charge transfer, for you to explain the trend in their band, you're actually going to use the same trick, right? So the first thing you need to take note is that energy is inversely proportional to the wavelength, right? So therefore, the more stable the bond. So in the case of we have Mn, let's look at the bond. So we have MnO₄ minus and ReO₄ minus. So the more stable the bond, the greater the energy required to break the bond, right? And the lower the wavelength. So if the energy is high, the wavelength will definitely be low, right? So the more stable the bond, the greater the energy required to break the bond and the lower the wavelength. So now the next thing you need to take note is that a stable bond is formed when the metal and the ligand are reactive. So if we are going to have a very reactive metal and the ligand, then the bond is going to be strong. So a metal is reactive when it is easily oxidized, right? So you need to note this, that a metal is reactive when it's easily oxidized. So a reactive metal is found lower in the periodic table. So basically from the schematic diagram, we said this is Mn and this is Re, right? So they are on the same group in the periodic table. So basically Re is going to be more reactive than manganese, and so therefore this is going to form a stronger bond, right, than this. So this is a weaker bond. It's not a weak bond, but it's weaker compared to this. So this will form a stronger bond because the Re is very much more reactive and it's easily oxidized than the manganese here. So this is a stronger bond than this. So this one will require more energy to break the bond, and therefore we have a lower wavelength, right? So this we have a higher wavelength. So looking at the question there, so we can therefore see that this higher wavelength belongs to manganese compound here, and this other one belongs to this, right? So take note of that. First of all, the more reactive the metal, the more stable the bond is formed. The more stable the bond that is formed. So also take note of the fact that it requires greater energy to break a stable bond than a weaker bond, right? So energy is inversely proportional to wavelength. So because this is a stronger bond, it requires higher energy and lower wavelength. So that's basically the answer to this. So, but in your exam, always specify this. Also, always include this, right? It goes beyond you telling them that the metal is reactive. You also have to tell them that it's easily oxidized, right, compared to the other metal. So here's a periodic table. So we have the group for manganese, and we have this the other compound here. So a ligand also, let's look at this. We said that a bond becomes very strong, right, when the ligand and the metal. So this is the metal coordinated to ligand, right? So the bond becomes very strong when the metal is reactive and also when the ligand is reactive. And we'll be able to see that a reactive metal is easily oxidized, right, and is found down the group. So also a ligand is reactive when it is easily reduced. You need this also when the ligand is easily reduced. So a more reactive ligand is found upper in the periodic table. In most cases, the ligand in most cases are non-metals, right? So they are found. A more reactive metal is found at the upper parts of the periodic table. So now let's look at this question. So basically, this the metal here in this case is constant, right? The metal here is constant. So now we are left with this the ligand here. So looking at this, we said the other time that a more reactive ligand is found at the top of the periodic table. So because chlorine, bromine are in the same group, we have chlorine, we have bromine, we also have iodine somewhere there. So this is the order of the reactivity, right? This is the order of the reactivity. So basically, this is more reactive than this, and because the metal is the same, this will form a stronger bond than this, right? So this is a stronger bond. This is a weaker bond, right? So this will require greater amount of energy to break the bond. High energy, let's put it there. So this one will require lower energy to break the bond. So because energy is inversely proportional to wavelength, right? So this one will require a lower wavelength compared to this that requires a higher wavelength, right? So therefore, we're going to say that this one will have higher wavelength compared to this, and so the reason is that Ca is more easily reduced, right, than Br. So you can also say that Cl is more reactive than this as well. So these are some of the reasons, because reactivity increases to the top of the group of these halogens.